Okay. So guys, let's start. And let's start with graphs. Maybe you can start with graphs. No? Here. Okay. So let's talk about. We can wait. Okay. Maybe I will talk about the extent. So the what is 7.1? Okay. So we have a graph. I think you all already know what's graph. Do you know? Yes. How to store a graph and in PFS. Okay, good. So the things to mention. First, this is Dijkstra. So you can have a single or multi-source shortest path algorithm with this, and I have the template. This is my template. You can substitute it with yours. I will do it with Politecnico. I think it's the fastest way. No? Yeah. Okay. And yeah, this part I'm just handling the sources, just single source or multi-source. Then I have the thing there. And let's also go to my GitHub maybe again. Graphs. Yeah. Maybe OpenPFS. Yeah. Okay. So actually, we have to start with BFS. BFS is the main algorithm for finding a shortest path, and it can appear in different ways. So this is a normal BFS, multi-source or a single source again, and this is again the best implementation. This is the faster one. Instead of having a queue, I have an array here, and I have 2 pointers and an R. I'm just doing every stuff on that. And the things that you have to remember for BFS, first of all, this is the normal one. Then we have some other kind of BFS, like BFS 01. So when do we use BFS and then we use Dijkstra? The answer is simple. Dijkstra is for the graphs that have weighted edges. Okay, but there is a case like I mean, if the weights are 0 or 1, either 0 or 1, we have a special kind of BFS, which is BFS 01, and you don't have to do Dijkstra actually. So basically, you keep the queue, and instead of always putting things at the end of the queue, with the 0, you just put it at the front of the queue. Did you get it?
It's like this 01 case, just like a normal graph, but you don't insert.
Yeah, you just compress it. Yeah.
Yes, we don't insert the edges that with
Yeah.
You do a normal BFS.
Yeah, but you should also compress them, right? I mean, they should be somehow compressed to form a single node.
Yes.
Yes. An easier way to do it is just not doing that, because for that you need DSU or PFS to connect all of them. So you do it like this. And so this is BFS 01. I didn't put this in notebook. I just mentioned it just for you to prepare you for the BFS levels. So basically, the other one. Sometimes it happens that you need a faster shortest path algorithm than Dijkstra. BFS is linear, and the other one is n-log-n. So the thing is that if you know that the distances of the node are in order of n, instead of doing the Dijkstra, you can have a level vector that you're seeing it there, and you can do the BFS with this level. This is called BFS with levels, and then something like that. I don't know if you got it or not. No? So basically, we have a level vector for each distance. Okay? And so the sources are all in the level 0. And each time that we are relaxing the neighbors of a vertex, we just append it to the current level. And then the iteration, when we want to find the next one, is just continuing on the current level. If there is still another node on the current level, we give the priority to that one. Okay, this is a small trick, but maybe it would be useful in SWERC because maybe you guys start to be in some cases slower. Maybe you have another factor of 10 and wanted to optimize this. So did you all get this? Okay.
Like 0-1 meter pass is just going.
Okay. Yeah, I mean, I mean, like having the normal queue for BFS, we always had the new nodes to the end of the queue, right?
Yeah.
But now you can add in front of the queue the ones that have 0 edges.
That's 0.
Yeah.
Okay.
Because they have a high priority of all of the rest, right?
Okay, so 0 of the value.
Yeah, and that's what I did here actually. I mean, I have a queue which is 2 max n, and I start from the middle LR max n, and sometimes I append to the right, sometimes I append to the left.
Okay. And like, when is this useful?
It's linear, so it's faster than that.
Okay, you want to like find the path with all the zeros.
I mean, if you could either do this
Or the zeros that don't have a weight, so
yeah, or a messy DFS and DFS combination, because each time you reach a node, you do a DFS with all the zeros.
okay.
But this is, I mean, I said this one to actually prepare you for the levels, because levels is just making this algorithm more general. We just know that the depth of the vertices are up to max and something like that. And so these are the main blocks. Then always, so there are DFS and BFS, and the important, maybe I should move this here. Okay. So in graph problems, okay. DFS3 and DFS3 are important. I mean, let's review some facts about DFS3 and remind me if I missed anything. Let's consider that we have a graph, and then we did the DFS from one random like R node, and we save the DFS3. What are the facts that we have? The first fact is that we don't have cross edges. So basically, every edge that is in the graph and it's not in the tree itself appears as an edge from a parent to one of its children, right? So it's always like back edge. So all the edges in all the extra edges in DFS3 are back edge. And yeah, the other important thing about the DFS is the tour, Euler tour, which I mentioned earlier, but I will repeat. So the thing is that you actually save the order of the vertices that have been visited in the DFS order. So let's give names to this one: 2, 3, 4, 5, 6, 7, 8. Okay.
Is this BFS?
No, this is DFS still.
Oh,
Yeah. And so the Euler tour is starting from this 1, then we go to 2, 4, back to 2, 5, back to 2, back to 1, 3, 6, 7, 6, 8, 6, 1. This is the Euler tool call. I think you've understood how to implement it. And this, the main fact here is every subtree in the tree is a range here. And each range here is a subtree. This is really powerful because also considering any range, the minimum depth, the vertex with minimum depth is the LCA here, lowest common ancestor of all these vertices. Okay, so this is really powerful. And This is not for me. And yes, so the other way to see these things are with starting time and finishing time. So basically, the time that we implement the DFS, and we have a timer. Each time we enter a new node, we just increase the timer by 1. So we are assigning the starting time for each of these vertices. So for example, for this one is 1, then this is 2, then this is 3, 4, and then this is 5, 6, 7, 8. Okay? And the finishing time is the time that the DFS of the sub-tree is finished. So for example, here the finishing time is 8 because it takes all of this. For this is 3, 4, so it's 4. Because after the time 4, everything is finished. I mean, we get back to 2. Again, for this is 5, 8. For this is 6, 8. 7, 7, 8, 8. So again, a starting time and finishing time here are kind of like the Euler tool, but in the Euler tool, we had like 2n elements, right? Here we have n elements. I mean, we don't, when we are going back, we don't re-mention the nodes, okay, when going up. Okay, did you get it? Okay, so you did understand this one. Okay, there is also another way for the Euler tool that we have is like this. So let me show you. 1, then we go to 2, then we go to 4, then we go back to 2, but we don't write the 2 in the array because it's useless. It's complicated. Then we go to 4, 5. Then again, we go back to 2. Don't write it.
Okay.
Don't write it. New one. 3, 6, 7, 8. Basically, this is the array, and the starting time is the index of these vertices in that array. And the finishing time is the time that's like here, we go here and here, and we come back after the 8 second, right? So the starting time and finishing time are those indexes and can help us with many things. Like they can give us many facts. Like if we have a P and we have a U in its children, in its subtree, we have this fact that STM of P is STM of the V, and I mean so we have this fact. The fact is that the children have this starting finishing time interval always contained in their parents' interval. It's obvious, right? So basically, this would be easy. So it's really easy in constant time to easy if a P is parent or parent is called parent, not a direct parent. It's part of another vertex. So basically, STM and FTM are really useful. And if I remember other cases, other facts, I will tell you maybe during the lecture. Then, so do you have anything to add on DFS? No? Okay. Maybe I can also say mention into DFS. Simple. Then let's talk about DFS 3. So always, I mean, it's always funny to also consider the trees of the famous algorithms. I mean, like the DFS tree has those properties. DFS tree has different properties. Again, we have DSU. I don't know if you know that. We have a DSU tree. Again, maybe you know or not, but it has some properties, and I mean, it's always useful to keep the tree in mind. So BFS tree. So in the BFS tree, in the like, let's say that we have one source because it's not that different. Then we have the levels, level 1, level 2, level 3, 4. So basically, if you consider, so these are the levels, which are the distances from the source. And the thing is that every edge in the graph is between one of two consecutive levels. Because if it's not, we could just push them and have a shorter distance. So this is also a strong fact that all the edges appear here in the BFS. Then what other facts do we have? But for BFS or generally any shortest path algorithms like Dijkstra, BFS, and BOOS, we can have a DAG, directly acyclic graph. That is like this. I mean, it's not a tree because maybe we have more edges.
What is that?
A directed acyclic graph. A graph which is directed. I mean, because there is a way to update all of the distances, so we can always consider this is a directed one, and we can keep for each vertex the parent, like the one that it got updated from that one. This way we can find the shortest path really easier because each time we can't. So here we have B, then we go R of B, have R of B. So these are also cool. We can do the same Dijkstra. Sometimes we also have a DP on the graph itself. So and constructing the sample of DP needs the same thing, like saving the parent for in the DAG. Okay, so saving the DAG of BFS is important. Then let's also show Dijkstra, but I think it was it's project group, and I'm not saving the DAG. So let me see. Yeah, any other facts? Maybe.
Not really.
Okay. So let's go to background mode. So now Bellman-Ford and Floyd-Gaucher. So let's say that we're going to have all pairs shortest paths. We can do one of these two algorithms, which let me remind myself. So for this one, we have a like DP of UB, or this of UB, and which is saving the distance from UV, and each time so we have all of them initially equal to infinity, and we add nodes one by one, and when we add the nodes, like we consider all the pairs that are there, and we update or relax their DP like with this path. So DP of U1, U2 is equal to minimum of itself, and sum of DP of U1, V, and V and U2, okay? So basically we have a N3, N³ algorithm to get all of the shortest paths, which you can see here, okay? And by the way, you see that here, the rep is the for iteration. The first parameter is the pointer of the integer that we are passing. So here we have for with k from 0 to 1, for of y 0 to 1, for of j. And why it's not I, J, K? Because if you put it this way, it's more cache friendly. Because here you
Actually, it doesn't work at all in visual theory.
no, it works. What? Yeah, I think so. Yeah, I think so. Yeah, but anyway, I mean, this is cache friendly and it will be faster because I mean we are respecting the order somehow. Yeah, I think maybe not that one. Okay, but that's the average for all the pairs. It's N³. You can copy it in the context that appear. The other one, Bellman-Ford.
Negative edges.
Hmm?
Just negative edges.
Then like straight if you have shortest path if you have negative edges.
I mean, both of them would work with negative edges. Right?
Yeah.
So I think in Dijkstra or any or VFX, I mean, we don't have negative edges. But if we wanted to, so let's say that we have negative edge, we could also have a negative cycle, which finding the short path is, I mean, nonsense. So in those graphs, we should make sure that we are finding if the graph has a negative cycle or not, and the main keywords to do that are Bellman-Ford and Floyd-Marshall, mainly Bellman-Ford, because so here we are running an algorithm for a limited time, and if after like an iteration we are relaxing something, let me just remind myself. So we have, so it's still from a single source, right?
Yeah, Bellman-Ford is single.
Okay, and we update all those and time. So it's VM. Okay, so basically it's a single source algorithm, not for all pairs, right?
I guess it can be like multi-source, but then it's the shortest path from any of these sources.
Yeah, I mean, it's not all
pairs.
pairs. Yeah, it's not all pairs. So again, let me say Bellman-Ford. So you have set of sources, and you want to find the shortest path from those to other vertices. It can be a single source or multiple sources. But the point is that, so for each vertex, we again have a DP for stance of that vertex, and we want to update it. So initially, all of them are infinity. Okay? And each time we add the edge, and we relax the DPs of two endpoints of it. I mean, like adding UV with weight W, we say DPU is minimum of itself, and DP of V plus this, and DP of V so adding each edge has this relaxation. Okay, we add all of the edges, and we relax all of the everything in the graph, but we do it n times, right? So basically, the order would be n, which sometimes, because n can be of order of n squared, it would be around q. Okay, but it's n usually. And the trick is that, so we add all the edge and do these relaxations for all the edge n times, okay? And if even after the n time, still there was the relaxation, it means that we have a negative cycle. Because if there is no negative cycle, after n iteration, n times doing this update, all the distances should be finalized, and there shouldn't be anything that can be done. Yeah, but this is the way to find negative cycles, you know. If we don't have a negative cycle, sometimes, I mean, we can do even less than that n times running the algorithm. Maybe
I don't remember. Dijkstra doesn't work for negative cycles, but negative edges.
Yeah, if there's no negative cycle. Yeah.
It can work, but worst case, all quadratic.
Yeah, quadratic.
Oh, okay. So it shouldn't be used.
Yeah. So basically, this is Bellman-Ford and Floyd-Marshall. Then maybe the last one, topological sort, right? So again, so let's consider that we have a directed graph, which is acyclic. We know that we can find the order of putting these nodes in a row that all of the edges are from left to right. This is topological sorting. And for finding the algorithm is there, but it does it with DFS and all the other stuff. So when we have a DAG, we can do the topological sorting. If we have a general, did you get it until now? Okay.
Yes, I didn't understand.
So did you get it?
No, I don't understand what you said.
Okay, okay. If we have a DAG, we can run that algorithm to get the topological sort, which is just the order. Okay. If we have instead just not a cycle, so we have a directed graph. Okay, it can have cycle. So the thing is that just consider the maximal strongly connected components, which means that you can go from each vertex to each vertex and go back. Okay. If you consider those maximal components, you will have several ones. You can like squish each of them and consider them as one node, and the resulting graph doesn't have any cycle, so it's a DAG. Okay. So basically, if we find the SCC strongly connected components, we can kind of have a topological sort of the rest, and I mean, in some problems, this comes handy. Okay, so now having a topological sort, we can go to the SCC algorithm. It's the next one, right?
SCC?
Yeah.
I think there's
Maybe you can find some like it one. I don't know. So you can think for you can think how we can do this for a DAG to find a topological sort with a DFS or something. It's a good beginner task. And yeah, but you can also use it as black box. Yeah. So for the SCC, the thing that we do is kind of the same. So we basically let me just revise. So yeah. Basically, instead of doing the normal topological sort, which is there here until here, it's not to get the topological source until here. You can reverse it for the. Then, I mean, consider the topological sort, and for this general graph, we know that it has some cycles, but I mean, the topological sort is telling us that all the eggs are from left to right, for example. The trick is that to start from this one, the last one, and do a kind of EFS to understand the whole component, the vertices that it can reach, and this would be the last component of the SCC. And we can just remove it and continue the other part. This is the whole idea. So basically, what you need in SWERC. In SWERC, you can run this algorithm, and each time that we are here in this part, we have the CNT++ and then doing the SFT, which is the reverse of DFS, and with the ADT and the reverse of the edge. You can say the component of each vertex. So you can understand for each vertex which SCC component it's belonging to. And this may be useful. This is the SCC in high level. Then
I don't know if you said it, but here the algorithm for the topological sort is not the same as the one on KCPL. The one on KCPL does not put node in the topological order if they're a part of an SCC that is not the node itself. So you have to be careful with that.
okay.
And in this case, it's just doing the DFS and adding when you finish the DFS from some vertex. So you consider the exit time.
Mm. Okay. All right. What's the next one? Close. So again, let me tell you the famous problem solving, and just leave it there. So basically, we have a directed graph, and should be that.
Not necessarily.
So the thing is that we have some eggs, like pipes that water can go through. Okay, and each of these have a limit of the amount of water they can, the amount of water that can go through it in a second. And we have a source, and we have a city. Okay, and we have these things. Okay. The question is, if you have an infinity water flow here, what would be the water flow going out in the sink? Considering all the limits of the pipes. Right. And so this is the maximum flow. That's why it's called maximum flow. Another way, which is, they are equivalent, another problem, which is equivalent to this one, is that having the same graph, we want to partition this graph into two groups, A and B. So we are partitioning the nodes into groups. Each node should be exactly one of these. Okay? And cost of this division, this separation, is the total cost of the edge in between. So V1, V2, V3, the total cost. Okay. So this is the cost of separation, and we want to minimize the cost of the separation. What is the minimum cost of this cut? Because we are like cutting. So this is a mean cut problem. Okay, and apparently these two are equivalent. So the value of max flow is exactly the value of mean cut. It's easy to show that the max flow is less than equal to mean cut, because if you consider the water all came here, and at most this amount can pass through here in this cut to go there and exit from the sink. And the other way is not that hard to prove, but these two are equivalent. And this flow algorithm, I think there are different flow algorithms here, but they are all solving something like this.
I think the mean cut can be like edges going to the left and they are counted as a negative, or
No.
all must be on from left to right.
Yeah.
In the template, you can specify the reverse capacity. Like normally, when you add an edge in this template, it's directed.
Okay.
But you can specify a reverse capacity. So you can specify that flow can actually go the other direction.
Okay, but like, I don't know if I understand the problem correctly. Like in the program of Mika, you have a graph and you have to split the nodes into groups such that the removing that is minimum.
Yeah.
Removing
this
the sum is minimum.
Yeah.
But and you count them in absolute, like there can be going from right to left, but you count them as positive. Or
So for the other one, I think they can be, but we don't consider them.
This Jiakai means if it's going from right to left, you can consider negative from left to right, right?
I am
not sure. I think not.
Yeah, probably it counts as negative if you just use a flow algorithm.
No, I think I think we can keep all of the values on the edge positive. If you have
Yeah,
a,
but the value is positive, but
Yeah,
like in terms of that being the mean cut, is
yeah, I think this is not considered because I mean, also again because these are equivalent. Having another pipe here going from right to the left wouldn't change the max flow in that row. So no, we only consider the edge from this part to that part here. Ignore the rest because I mean, it doesn't make sense. And I mean, you can reason like that because these two are equivalent.
Yeah, because it's like if you are thinking it's on the left, you are just thinking more back.
Yeah. Exactly.
Yeah, this one is very important. Usually there are some problems that have like very high constraints, but they're very easily modelable as flow problems. But usually you cannot do flow, right? So at that point, it's a lot easier to think about the minimum cut.
Okay.
Calculate the maximum flow because there's usually.
Yeah, and so now the algorithm itself,
I don't know.
is this the main flow algorithm? No.
It should be. It should probably below.
Maybe in my part also have flow, I don't know.
Oh, wait.
No, I don't have the flow implementation. But dynamic. Max flow energy. Yeah, that's the one I put actually. Energy is one. So where are we? Okay. So I don't know the push reliable. I don't know
Label. It's push label. Like you label stuff like that.
Okay, relabel.
Yeah, and this first.
I think I should also calculate. And I think these two are useless, no? Because you can always use that one to always faster.
I don't know. But math flow is a bit different. Unless it's like same as yours. Yeah, I don't know.
Okay, so there are different problems here. Mean cut max flow that they are mentioning, I think, is the same thing that we mentioned, and it's solving the same problem. And calling this function max flow will give you the answer. And I mean, these are different algorithms with different complexity based on number of edges and number of vertices. So the complexities are different. But I think the one that I added, just ignore the complexity there. It's not correct because I just copied it. I think it's L again. So this is the actual current flow algorithm that we can use. Whether we will update our notebook so other students can also use it. Also, there is mentioned that mean cut is actually the max flow, and the global mean cut.
I think this is comparing algorithm.
So it's entry. It's like the DP algorithm, right? Okay. Yeah. And the agency matrix. Okay. Yeah, this is also the global mean cut. I don't know what's the difference actually. But I think this is enough for the SWERC teams and this is for not anything more. Then Bomoriho, I don't know what is it. Do you know, Jiakai?
It basically creates a tree to calculate math flow for every pair of vertices.
Ah, okay.
Yeah.
And the complexities?
It's just the amount of flow computations. Which should be the number of edges, I guess.
Okay. Nice. Okay. Generally, the original flow algorithm that my template is showing is n log m, but in the other cases, you're solving.
But
I think it's, no, I don't remember, but I don't think it's linear. It should be pretty bad, like complexity wise.
The flow one,
Yeah, flow is not that fast.
really?
Yeah, it's not linear. Like it can kill problems. I mean, it's on case here, like it.
Okay.
I mean, we can check it out.
But yeah, let's check it now because I think.
what is the equivalent of source and sink? Like, since they are technically the same problem, you did in that way.
What is their difference actually? I mean, because
like
the direction of the edge that we are summing up depends on the decision we made with the source and sink. So maybe that's your answer. I mean, you're fixing the direction.
But like, there is no SLT in the bean cut problem, right?
I think it is because S should be always in this set and T should be, yeah. Yeah, I think it is, yeah. So
It should be square root of b and t, and it's something that there is a special method. I don't remember the.
really? Okay. So it's square TVE.
Yeah.
Instead of n log n is like if you have many edges, it's n2 half.
Something like that.
Okay. We should actually also I think we should add it to the notebook. The one that you should.
Yeah, maybe we can remove push label. Not sure because I never used it.
Okay. Then, so also another thing which is related to this stuff is matching. So the matching problem is so we have let's start with the bipartite one because the other one is NP, if I'm not wrong. So we have our bipartite graph and we want to find the matching, the maximum matching there. So basically there are different algorithms to calculate it, but the main one is Clinic. I had it there. This one, yeah, doing many DFX. So, but what is not ignore the matching method because it's not important. And so here, just giving the graph, it will give you the matching with the top cross graph matching, which is of order of this order, which is not bad. And what else on matching? Okay, the matching problem can be also solved with flow, because I mean, consider the arcs. We add a source. I mean, we add two vertices, one with source, one with sink, and we connect it to all of these and all of these. I think all with infinity, right? All with infinity. And now
We also want to be the same because you're picking like every edge one.
oh, maybe yeah. I mean, it's not different.
No, it actually should be one.
Okay.
Because maybe you have multiple edges from the same.
Okay. So also this.
Yeah.
So sorry, the it should have a weight of 1, and actually I mean, here we have the actual graph, actual bipartite graph, and the maximum flow from source to sink is likely the maximum matching, right? And the weights of the edge here are also 1. So basically, with flows, if you have an algorithm to solve flow, we can also find the maximum matching. Any question? Did you get it?
Why?
Because we have so we have infinity water here. All the pipes have vertical.
I understand you, the source is like another things that we are adding and we are connecting it with.
Yes, source with one side of the bipartite and sink with the other side. And we are giving the direction of like this.
Okay, so we are connecting it to every vertex.
Every vertex in one of the parts in the bipartite graph, right?
Yes.
And the other one to the other one. So I mean, all the water that is passing from the source to sink should go through our graph, which I mean, because we have the limit 1 here, so at most one of these would come to here, and then at most one go there, so it gives the maximum matching.
Okay, yes.
Yeah. I think this is not a formal proof, but the intuition.
I don't know if it's formal, but that's how I put it.
Yeah. So, yeah, this is also the matching. The other important thing about matching is one theorem. I don't remember the theorem name. Maybe you do the next term.
Phoenix theorem.
Yeah, conic, right? So I don't remember the actual the main statement, but it's like this. Do you remember the next?
Basically says that in a bipartite graph, the maximum matching is equal to the minimum vertex cover. But I don't know how to put it.
By the way, just to be sure, what is the definition of maximum matching? Given about bipartite.
Maximum matching is the maximum amount of edges you can take in a graph, such that every vertex is connected to at most one of these edges that you take.
Okay, yeah. So the maximum matching is equal to minimum vertex cover. The proof was not that obvious, but it was not.
Dilworth theorem.
Dilworth?
All process. It's not obvious at all.
Yeah. So isn't it called conic?
No, this is conic, but the proof is done by Dilworth theorem.
Ah, okay.
It's another thing that related some properties of posets. You know, posets?
Yeah.
Like the length of the maximum chain,
Yeah.
okay, is equal to the length of the minimum ant chain. It is
Yeah.
not connected elements. It is the same essentially, and you have to apply it in a sneaky way here.
Jiakai, you should study this. Yeah, but so this is important. This is really important. 2 years ago, I saw one problem like this. I just knew it, didn't know the proof. Also, the other thing is that there was something related to independence.
Yeah.
I know that. I mean, if you take the matching here, the maximum matching here, we don't have any edge here. Okay, so this part is a candidate for being the maximum independent set. But I mean, it's an independent set. So maybe you can say IS is more than equal to. I don't know if it's exactly equal or not.
But this IS.
In this, okay, biggest, right? Yeah, that's biggest.
Like not connected.
Yeah, no,
separated, components.
Yeah. So consider a graph. The largest independent set is the largest set that we have. So, I mean, I'm just telling a fact that is if we take the maximum matching we know that there is no edge here, because if it was there, this was not maximum matching. We could also include that one to the maximum match. So there is no edge here. So this is an independent set. So the biggest independent size, let's say it like this, is at least n minus 2 alpha, which is the matching size. Maybe you can look it on again. Is it exactly, or is it just lower bound?
What? Okay, maybe I don't remember. Oh, it's minimum. No, wait. It's not different.
Independent vertex set, I think it should be. Not edge set.
Yeah, there's
Okay, for matching. Okay. Okay.
Oh, okay. So no, it's complement is the vertex cover, so it's not the maximum.
So if its complement is a vertex cover, this is an equality.
Yeah. So yeah, if and only if its complement is a vertex cover. So
So the complement is always a vertex cover. Doesn't make sense to me, actually. I mean, the complement of that one is the whole match.
If the vertex cover, we have an equality, right?
But I don't think it's it is.
Why not? You just take like all these couples and that's it.
Yeah, but that's an upper bound for vertex cover. Because
You cannot take one single edge, right? You have to take at least two, and they are connected. So these are
I mean, when we say the maximum matching is equal to minimum vertex cover, we mean that if we consider that here we have alpha vertices.
oh wait, they're complements. So I mean they would solve the same problem. Minimum vertex cover is a complement of maximum independent set.
So, what's the relation in mathematical sense?
But it's maximum independence. So it's maximum, it makes sense, right?
No, I mean still. So,
Oh, if you take the maximum independent set,
okay.
and then instead of picking the vertices that make the maximum independent set, you pick all the other vertices, that's the minimum vertex cover. Right? Because if those vertices were not part of the minimum vertex cover, you could take them to make your independent set bigger, I think.
I'm not sure. This is GPT.
I mean, probably to be true for those graphs. That's not only like that.
Yeah, probably, yeah. What was it exactly? So, what's, yeah. Yeah, so minimum vertex cover is a complement of maximum independence set. That's true. And okay, so that's an equality, right?
What is that? This is only valid for hypertype graphs.
Okay.
Yeah.
But I mean, there, yeah, is it an equality or
What is BIS?
biggest independence set, let's say? Maximum independence set.
Don't know.
Let's.
I mean, either way, I don't think we're ever going to get a problem where we need to think about these relations for a non-bipartite graph.
Yeah.
And for a bipartite graph, they should all be equivalent problems.
Yeah, exactly. Yeah, I mean, and knowing this fact is enough. I mean, I solved many problems just knowing this. That, okay, if you take the maximum the rest is independence and knowing that these two the conic theorem. Yeah, but I think I don't know, Jiakai, maybe can you later in the group send something related to this?
Yeah.
Okay, nice. Then okay. Let's skip the matching part and DFS matching. Is that? Yeah. No. It's the same algorithm for the. And we also have these things that you can read.
Oh, yeah, it was written here.
Yeah. Okay, nice. And the complement is a maximum independence set. Okay, nice. So basically playing with these facts, I think it's enough to solve problems. And then here we have the DFS algorithm SCC I covered. They like connected components. Yeah, nice. We can do that, right? Yeah. Okay. We should also have the other thing. Two connected.
This one?
Two connected things. Do you remember?
No, it should be the same.
This is that one?
Yeah.
Okay. If it's that one, I think. So, we haven't graph. It's really theoretical. I'm not really the best one to explain. But let's consider that we have a graph, and each we want to again divide the graph into some parts, which we want to partition it. That each partition is bi-connected. But yeah, it means that if we remove one edge from it, the others are still connected. Okay. Or in another way, is there something like all of them are in a cycle, so there are two ways to go from each vertex to other one, which both are completely disjoint. Okay, so basically, maybe I can show an example, or maybe you can. Jiakai, can you search it on the web? Just by connected components, and there would be a clean example to show. Yeah, this one is the. So these are the bi-connected components. So as you can see, the red ones have all these properties. So from each one to another one, there are two disjoint paths to follow. And it's equivalent to say that if we remove any arbitrary edge, still the others are connected. And I mean, as you can see, it's not like that each vertex has a single color. Like here, the components are a bit weird.
Like the blue, like the pink one. If you remove that edge, they aren't connected anymore.
right? But I think
Yeah,
it just
it refers to node, probably, to node removal. Like, I think there's two connected components when you remove a node and when you
remove a node, not an edge. Okay, okay. Sorry, yeah. If you remove a node, but it's still.
It's probably
And the other one is bridge. Okay. So basically,
If it was only removing edge, it would have been
like the normal DFS, yeah.
from bridges.
Yeah. Yeah.
I mean, we can look it up when later.
Yeah, okay. And I think that's it for that part. The other thing is TwoSat. So basically, for TwoSat, we have some expressions, like, I mean, that we know that are true, like, we know that P or Q, we have some expressions like this in the graph, not in the graph, generally, okay? And we map these things to a graph and we do something. So what we do, let's say that we have n variables, like A1 to AN, and we know that they have some properties, like, you know, that A1 is, we have a condition that like this, that should be satisfied, which is like A1, A2, one of them should be at least true, something like that. The thing we do to solve it is we create a graph with two n nodes for the normal vertices, and another set of n nodes with complements, okay? And basically, we add directed edge from U to V with the definition that if U is true, then V would be true. Okay, so if we have a directed edge from U to V, it means that if U is true, then V would be true. Okay, and we convert all of the conditions that we should fulfill to this graph explanation, this graph mapping, I don't know how to say it, modeling, yeah, and then, so let me give you some examples. If we say that A1 or A2 should be 1, it's equivalent to say that if not of A1, then A2. So if this is true, then this is true. Or this. So these two edges in our graph mean this. Because I mean, we say, okay, if A1 is not true, A2 should surely be true. If A2 is not true, A1 should be surely true. This way we are ensuring that at least one of them is 1. And or if we know that AI is equal to 1, basically what we do. So I don't know if we know A1 is 1, what we do? Oh, okay. We say that if A0 is true, no. Sorry guys. AI. So this edge is telling us if not of AI is true, AI would be also true. I mean, we would have both of them true. This is a contradiction. So this way we are ensuring that to avoid the contradiction, the only way we have is to put AI equal to 1. I don't know if you got it or not. So basically, all of the conditions we have, we translate them to the graph definition of them. And then we have an algorithm that finds out if it's possible to respect all of those rules. Okay. So basically, let's suppose that we have that algorithm that would ensure that all of these conditions are true and would give us an answer or tells us if it's impossible. Okay. Then, if we want to force that algorithm to make AI equal to 1, make AI equal to 1, like make it true, we say that A0, if A0 is 1, A1, AI should be also 1. I'm really explaining really well. This way, the algorithm cannot avoid the contradiction unless it makes AI equal to 1 and AI not equal to 0. Really bad. I think you didn't understand, no? You got it?
If not AI is true, then it's a contradiction. So when you find, like when you search for,
so we are forcing that.
you can that, but
Yeah.
that can not AI can be true.
Yeah, yeah. Did you also get it? Oh, you no, you didn't know. Okay, no problem. So I will cancel some stuff now. So the thing is that we have two end nodes. These are the not of those ones. And basically, we are translating all of the conditions we have, like P and Q, into our graph for P or Q or P and Q. Okay, we translate all of them to the graph conditions. And in the graph, an edge in our graph from U to V is saying that if AU, then AB. If AU is true, then AB is also true. This is the definition in our graph. Okay. Now we have an algorithm. For now, let's forget about the algorithm, what it is itself. But the algorithm will tell us either it's possible to make either it's possible to make for each pair one of them true, one of them false, to respect all of the rules that we have translated, and it will give us the answer on how to do that, or it's impossible. Okay. So now let's translate those things. Let's say that we have AI or AJ. In our graph, the translation is adding edge from AI to not of AI to AJ, meaning that if one of them is false, the other one should be true. So this way, we are forcing the algorithm to respect that rule. This rule. Okay. The other one, AI, AJ.
So you look for like a path, a directed path from A to B now. That is not it's okay.
Yeah. Yeah, exactly. And for the other one, AI and AJ, both of them should be true. So basically, the thing that we do is, okay, we say that not of AI means AI, and not of AJ means AJ. Meaning that if you assign one to the not of this variable, both of them would be true. This is a contradiction, so you fail to respect the rules, so it would be impossible. So unless you make this one 1, and this one 0. So basically, we are forcing it to put AI equal to 1 and AJ equal to 1. Basically, we have or and we can do all of the things that you can logically have. So we translate all of them, and we run the algorithm, and it solves everything. This is the whole.
For each node,
For each node in the and yeah, for each and command. Yeah.
So like doing like the end is like doing AI over AI and like splitting into AI over AI and AJ over AJ.
Yeah.
But how can you actually find like once you constructed the graph, like how do you find
So
it?
one thing is that so basically, so the graph would be a general graph which can have cycles, right? And so consider the graph directly graph.
And I think it's either all ones or all zeros.
Let me say. So this would be the SCC components of the graph, and basically the SCC component means that if one of them is 1, all of the component is 1. So each component is either 1 or 0. Okay. If you have AI and not of AI both in the same component, it's a contradiction. And that's it. And for the rest, we would have a DAG, and for assigning currently to a DAG, I don't know. I think you can just assign randomly, right? Yeah, I think. I think you can start. Thing, but I mean, this is the condition for being possible or impossible, and the code also works. So now this part, I should just
Really
revise.
randomly, but starting from the base.
Yeah. I mean, I think you can put this one as 1, and then check if this one becomes 1 or not.
Okay.
You know.
Yeah.
So yeah. So basically, consider A1 and not of A1. One of them is 1, one of them is 0. I think we can consider one of them 1 and the other one 0, and the rest of the things would follow because they are all connected. Yeah, something like that. Yeah. Okay. But the code works, so don't worry much about that part, and you can read it later to exactly understand what it does. This is good. And let's move on from the 2-sat. The other one is Euler one. So okay. So what is Eulerian tool? It's a bit different from the thing that I said for 3. They have the same name, but these are 2 different things. We call a graph Eulerian. Let's consider that it's undirected. Okay. We call a graph Eulerian if we can have a travel through all of the edges and making a cycle. It would be an Euler tool, right? I mean, you can visit the same vertex multiple times, but you cannot visit the same edge twice. So this is the Euler tool. And what's the condition which is necessary and sufficient for having Euler tool is that all of the vertices should have even degree. You can easily see that that's needed. Okay, and for being sufficient, again, it's really easy because for each vertex you just pair their edge 2 by 2. So each time you just came to this vertex by one of these edges, you just exit by the other one. And basically you would have an Euler tool. Maybe it's not connected, but if it's one component, it's connected. If not, each component would have a different Euler tool. Yeah. And Euler tool can be like this. I don't know if you see it, but I mean it doesn't matter. Like this joint looks. And yeah, this algorithm finds it. And also for you, it would be really easy. I mean, you just assign it like this, and you will find it. Okay. Then, so I mean, let's say what kind of problems that can have this. Let's say that we have some dominoes. I think sorry, something like that. Japan. We have some dominoes, and we want to put the. It's like a domino game that you should match the dominoes to be possible to put them together. Like, okay, and the problem is asking you. The problem is asking you to give a valid sequence of all the dominoes that you have. So basically, you have the dominoes, but you have to find a way to put them in a line. Okay. The way to do it is basically you should check if the original graph has at most 2 odd degree vertices. Okay. If there is none, it's okay. If there's exactly 2, you add a fake edge between those. Okay. Then you look for an Eulerian tool. Then you would have a tool which has your fake edge at some point. You just remove it, and the rest, this would be the thing that you're looking for. This would be the domino path that you're looking for. You all got it? Yeah, that's fine.
Yeah, but like if we the edges,
One fake edge.
no, like the other edges are just
For example, for this one, it's 3 to 1.
or the ones that. Okay, you just count them as done.
Yeah. I mean, each of these would be a vertex, and each domino would be an edge. I mean, these kind of problems appear when you map the actual problem to a graph problem. Like here, considering each domino as an edge, you would understand, okay, a chain of dominoes is actually a path in a graph. So you look for that one. Also in the matching problems. So usually you have a different problem and you model it to a graph problem, but there you have something useful. Okay. Then we have edge coloring. I don't know what's that. So not important probably. Okay, but that's really obvious. It's saying that if the maximum degree is D, you can color the graph with D plus 1 colors, which is obvious. You just go in a random way, and for each vertex, because at most D colors are burned, there is at least 1 color left that you can assign to that vertex. So I think that algorithm is just bullshit, not worth to mention. Then the maximum freaks, I mean, we have, yeah, maybe read that part later. I think it's not important. Yeah, the maximum freaks. Do you think it's important? Or do you want to read it right now?
How you could use it.
Hmm?
Never used it, or even thought of it.
Then the trees. So again, this is the LCA, lowest common ancestor. The way we do it is with binary lifting with parents. So we say all of the parents of height 2 to power k, and then finding the LCA with this algorithm. I think you already know the algorithm. If not, just black box it is just there, and it would be really useful to find the distance on the tree, because distance of U to V on the tree is distance from 1 to U plus distance from 1 to V, but we counted this part from LCA to 1 twice. So sum of these 2 minus 2 twice of distance LCA to 1. Really easy. Sometimes this idea appears like maybe you have an EP or something that you want to have the same structure, so with the same idea of only saving the values with jumps or lengths of 2 to power k. You define a TP of that kind, and you calculate the stuff. Like RMQ that we saw in data structures, that I was saying that RMQ of I is the minimum for the range of RMQ of I in K is the minimum of the range starting ending at I with the length 2 to power k. This is the same thing. Actually, RMQ and SA are proved to be equivalent. That's it. This for the and this one compressed tree. I don't think that would be useful.
It's a virtual tree.
Okay. You want to explain it?
It can be useful when you need to do DP on like different subsets of nodes. So you only care about like their LCA and stuff. So basically, it reduces. You start from a tree, you take a subset of nodes, and it just finds the set of these nodes plus all their possible LCAs. And the number of nodes at most is 2n at this point, where n is the size of the subset. And it can be useful sometimes.
Okay, nice.
I don't know if this is fair. I think it does.
Okay, next. HLD. So, Jiakai, maybe you can search HLD through internet. So, HLD is really funny. So, basically, you have a tree, and there's a way to color the tree that each coloring is a path from a parent to a node. Okay, you will see the picture. So maybe just three. Yeah, okay. So basically, you have a tree, and you are composing the tree into paths from ancestor to the children, from parent to children. Okay. So for example, this is one path. This is another path. This is another path. This is another one. Another one. Okay. The way that there is a special way to choose these paths that gives us one fact. And the fact is that starting from any vertex going to the root, you would see at most log n different paths. Okay, this is really useful. Okay, but how? Basically, the thing is that starting from the root, you have a path that came. Okay, starting from the root of the subtree, actually. Okay. This is really easy to implement and understand. So let's say that after some time, we came to the vertex U, which is the root of the subtree, and we know that there is a path coming to it, right? So now consider all of the children of this vertex, like V1 to V1, V2 to Vk. Okay? And consider that V1 is the heaviest one, like the one with the biggest subtree. Okay? We always continue the path that came into U to the biggest child. Okay? This is the way that we color it. Like here, we went to the 4 because 4 had bigger subtree. I mean, this is 5, this is 5, so we choose this one, no difference. And here again, this path, these children has 3 in subtree, it has 2, we go here and there. Okay? So this is a way to decompose the tree into several paths. And why is it good? Because basically, going from vertex to the root, just imagine the parts that the path is changing, like these parts. Okay? The other parts are not changing. The fact that it's not changing. But for these parts, the fact is that this subtree was larger than this subtree. So if you're here and each time if you consider the count of nodes in your subtree, moving to the other one, you are at least multiplying it by 2, the number of nodes in your subtree. So the number of times that you are changing the color, you are also multiplying your subtree by 2. At most, you have n vertices in the subtree, so at most log n times to change the color. This is really beautiful, and really, this is really strong. So, for example, you can put these paths in some array, and you can build some segment tree on that, and you can that way you can have a random arbitrary path from U to B arbitrary. You can decompose any path to 2 log n paths in your array, and in each of them you can solve them with the segment tree. I don't know if you got that. No?
Like if you go from red to green, you at least double, but what if you go from green to red? Like you are on a green path and you will go up to red.
So you are there, it's a green.
Like if you are on the green, if you are on the red and then you go to the green, then you double because like the other side is the same size. But if you are on a green and you go to a red, it doesn't mean it doubles necessarily.
So for example, here it doubles because this part is.
Yeah, but like from 5 to 2.
From 5 to 2, you are not changing the path.
Ah, okay. And it doubles?
No, it doesn't
yeah.
usually.
Oh, okay.
Yeah.
You know? Okay, yeah, I have to think about
Yeah. I mean, just consider here, the biggest child is not changing the path. The others are making their subtree twice the size. So for the others, they're changing the color.
Yeah, okay.
Yeah. So again, having this decomposition can help in a lot of ways. Like for example, really conceptual. Just imagine that you want to find the LCA of 2 vertices. The thing that we can do is to consider one of them and all of this decomposed path to the root. And for each of them, it's like an array that we can do a binary search on it to understand if there is the LCA here or not. So basically, we have a way to solve LCA problem with HLD. It's really easy. And we are using the fact that these are on a path really beautifully, so we can pre-process some stuff on it. This is HLD, and let's go back to the notebook. Then, so yeah, this is the code. The pre is the pre-process to calculate the heaviest child and the subtree size. Then HVS is the heaviest child. Then in the DFS, I'm just preparing to go first with HVS into the heaviest child. This way, the starting time assignment would follow the path decomposition I just mentioned. So this array of STM and STM in the underlying array is something that I can do segment tree or other things on it and pre-process some data and use it in queries. And this is the query part. As you can see, while b is not equal to 0, I get the root of the path. Okay, and then I do some calculation of anything, and then I change my vertex to the palette of the root of my current path. So like changing the color. So this is HLD. The other thing, link up tree is not important. Let's just forget about it.
In a bit, we'll have to.
Yeah, I think we can finish with graphs. I mean, DP and strings remain, but maybe I will record something.
Is there something important for string other than hashing root models?
AMP maybe. Yeah. But I mean, the hashing is enough. And so, directed MST. I don't know what is that.
Me neither.
So it's not important. Let's talk about DSU. Oh, we actually talked about DSU, right? So finding the MST is really easy with DSU. You sort all of the edges based on the weight, and you start from the minimum bar, and you just, each time that this is connecting something, it's in the MST. If not, not. This is the Kruskal algorithm. There's prime algorithm, pretty much the same, and that's it. Yeah.
I mean, actually,
Yeah, I think most of it, and KFT and all for in subject matter as much.
I just wanted to say that like there are some algorithms that can be pretty useful. Like interval container is very nice when you want to work with
Yeah.
there's signal properly, so you don't think too much about them. And maybe interval cover can be useful. I mean, just look at it. You need to be good.
Yeah, maybe later I could record the video on famous DP and string tricks just to be complete. But I think for strings you are already okay, and for the DP you just need a review on famous things like LIS, LCS, DPLR, DP on tree, and these ideas. That's, I mean, even in the last year recording there are some things. So yeah, let's conclude.
The simulation we did, which is the only one.
Yeah.
There was a LIS problem, and I remember it.
Yeah.
I took a lot of time because I had it wrong with the one.
Oh, yeah.
But it was
Also without
any other.
Yeah, Pasquale, thanks for coming.
Thank you, Nima.
Okay, are you up for a simulation tomorrow?
Yeah. Tomorrow,
We will talk about it.
Sunday. Yeah, no problem. In the morning, like 9 a.m. as usual.
Yeah, maybe 9 a.m. like usual.
Yeah, it works. Yeah.
Great. So see you later. Have a great time.
See you. Bye bye.
Bye.